Hi, my name is Joe Kramer. I'm a physics teacher and a writer on OpenSciEd High School Physics Unit 1. Lesson 11 is the last lesson of the unit, and we have an opportunity to propose solutions to our local energy grid that better meet the criteria we set from talking to our family members and friends. There's also a transfer task that we'll take a look at. So let's get into it. First, how we get here. We finished lesson 10 having identified trade offs of various different energy sources and talking to family members and friends about their top criteria. So we're wondering, how can we apply those ideas to analyze our current electric grid and make improvements? This is an investigation lesson that takes place over 3 days. It only requires about 30 minutes of materials prep. There is a video showing students how to use the energy grid calculator, which we'll look at later, and a video for teachers showing how to set it up. Setting up the energy grid calculator can add to the setup time depending on how much customization you want to do, but the bare bones setup should only take 5 to 10 minutes. I'll talk about this lesson in 3 chunks over these 3 days. On day 1, we first introduce the energy grid calculator. This quantitative spreadsheet model shows us where electricity in our state or region currently comes from, and we figure out that our current grid likely doesn't meet all the top criteria we identified by speaking to family members and friends. So we're wondering what we can do to improve that grid. Later on in day 1, and then continuing into day 2, we have a chance to make changes to our local grid using this energy grid calculator. And then we work to develop our solutions in more detail and then present them to students. So, halfway through day 2, we share our design solutions with students in other groups and get feedback. We figure out that it's impossible to design a grid that perfectly meets all criteria, so we need to prioritize, and different groups have prioritized differently. So that helps us give feedback to other groups about their designs. Then the main key moment in lesson 3 is the Santa Mira's transfer task. On that task, we figure out that there are some very unique new technologies that could help us deliver the electric energy that people need when they need it. In summary, we figure out that our electric grid currently doesn't meet all the criteria that our family and friends prioritized. We can quickly model the impact that changes to this grid will have, but it's impossible to satisfy all criteria perfectly. So we need to acknowledge trade offs and prioritize criteria. Some details about these key moments. The spreadsheet that you see here, the energy grid calculator, is a very powerful tool for estimating the impact that decisions we make about electricity as a society will have. We quantify reliability using 2 numbers. First, winter crisis in purple is an estimate of what percentage of demand will be met if a crisis like the one occurred in Texas occurs in our local region. Second, windless night in green tells us for how many hours people will have electricity if wind and solar drop to zero. We can also estimate carbon emissions and cost and land use. As students are considering the impact of our current grid in part 3, the readings from lesson 10 can give some qualitative detail about sources. If you want the most up to date version of the energy grid calculator, the tiny URL that you see here can provide that. The link in the teacher edition will also work. Note, setting up this calculator for your local region requires a little bit of doing, so I'll show you that later on in the video. In part 5, notice that making changes to our energy grid requires a separate tab at the bottom of the spreadsheet. So the current grid tab is all the way to the left. There are 3 different solutions tabs to allow student groups to compare and contrast their solutions. Make sure to communicate to students that they need to scroll down on these solutions tabs to demolish plants that currently exist, and then they use the upper yellow boxes to add new power plants. These two documents from Lesson 10, Energy Source Statistics, and quotes from interested parties, can be helpful for group discussions. The statistics that you see in this table are what the energy grid calculator is using for its calculations, and the quotes will give you a more human perspective on the decisions that we're making here. Then students present their solutions to each other for feedback. How complex these presentations can be will certainly depend on how much time students get to create them. But the protocol that's built into the lesson structures feedback in a way that allows some team members to circulate around the class and get new ideas, give feedback to other groups, while others focus on their own team's work. Then the last key moment in day 3 is the send and mirrors transfer task. Make sure to look through the answer key for guidance on scoring, and note that proportional reasoning using algebra is highlighted on this task. Students get that practice with that algebra on the testing battery storage handout from lesson 9. If a student missed that day or didn't understand that work, they may need to spend some more time with that practice to be successful on this transfer task. Then, depending on your plan for the year, you can go on from this lesson to Unit 2 about plate tectonics, or you can go directly to Unit 3 about car collisions and safety. You could even go straight to Unit 5 about electromagnetic radiation. Um, it's worth mentioning both Unit 3 and Unit 5 contain physics concepts that are more traditionally thought of as part of a physics course. Unit 2 is focused on explaining earth science phenomena from a matter and energy and forces perspective. It is definitely a physics unit, but it includes earth science ideas. Some tips and tricks. The background tab of the energy grid calculator is entirely intended for teachers to set up their energy grid calculator for their region before students make a copy. This means changing some numbers in yellow boxes related to city population and the area taken up by the city. Solar irradiance matters a lot for decisions about solar panels. For example, panels built in Maine will be less effective than the same solar panels built in Arizona because the sun is brighter in Arizona. Less important, but still possible to consider. Wind speed is different in different areas. Geothermal plants and hydroelectric dams can only be built in certain regions. So there are maps and other resources here for customizing the sheet that you give to students. If time allows, this project can be scaled up to include presenting solutions to real community members, or visiting a power plant, or asking a representative from electric utility to come in and answer students' questions. All of this takes time, but it can be very engaging and meaningful for students to see that these decisions that we've been talking about are very, very real. On the transfer task, providing students with transparent rubrics like the one that you see here can make your grading much, much quicker, and can be very motivational for students to see what they need to do to improve their understanding. That said, I have sometimes skipped this transfer task completely in order to spend more time on the design project. These decisions are entirely up to you and your school. We co-construct the meaning of design criteria and constraints in this project, and this is a great way for students to really understand what those terms mean. Terms like life cycle cost and land use are a way that these factors are quantified in the industry, um, to take into account the entire lifetime of a typical power plant. We encounter the term carbon emissions per person per year. And while we have defined reliability previously together, putting a number to it in the way that we do here is new. I always ask students to make an energy transfer model as a part of their project. and their presentation. The example I'm showing here of battery storage from lesson 9 tends to be a useful example, but students are free to use whatever example is relevant to their solution. The biggest takeaways from my perspective are real solutions to our energy needs are challenging and complex, but quantitative models can help us tackle them. It's worth mentioning while this spreadsheet is very complex behind the scenes, students only need to make changes to the yellow boxes. They tend to do that very intuitively. So, whether or not you spend a lot of time on the project presentation, spending time with the energy grid calculator is very worthwhile. Thank you very much. We'll have more videos about other units in the high school physics course, so I'll see you in those.